Okay, then we get started with today's morning session. We're very happy to have Massimo Taronna from Naples, and he will tell us about lessons for celestial holography from AdS-CFT. The floor is yours.
Thank you very much. So first of all, of course, I would like to thank the organizer for giving me the possibility to present our work. That is mainly the work of the Naples group. Here is a list of many people. Some of them are here. Unfortunately, I will not be able to speak about everything we are doing. Most of what I will say today will be based about these three papers, which is in various collaboration with Charlotte, of course, and Lorenzo and Francesca Pacifico, which is a PhD student in Naples. There are also various other results to appear, which I will not be able to focus on this talk, but if you have questions, maybe we can say something about that. So I was told that this should be a very very open seminar. Like, feel free to interrupt me when you want. And I prepared some initial part of this talk to give some basic details, like some kind of kinematics of the big picture that we are trying to go after. So the motivation is good to say, but I can understand that for this audience is a bit redundant, is that we would like to understand the holographic principle. And this is the kind of main idea behind this workshop and also the work I will be presenting today. And what I want to underline is that holography is kind of, so understanding holography is kind of equivalent to understand the axioms of quantum gravity. So, and this is kind of the perspective that I will take, that we have been taking in these works. And indeed, the most successful example, the most successful toy model of holography, which is AdS-CFT, precisely codifies these axioms in terms of OP and crossing. So we have an example, a working example of holography, where we do understand these axioms of quantum gravity, which are mapped to the boundary via holography. Crossing symmetry of the CFT. And basically, a set of OP, I will go into more details into this. OP is about analyticity of the observable. It tells you what are the possible singularities that can appear at a non-perturbative level. And crossing is a condition that you have to implement on the spectrum, so on the singularities, so that this gives you something consistent.
And then you mean Lorentzian OP, not Euclidean OP?
Yeah, here I didn't say, but of course, when when I talk about holography in the context of AdS-CFT is of course AdS Lorentzian. Yeah, when I mentioned this.
Okay, I guess it's okay. So for Lorentzian theory, the notion of OP is a little bit more subtle or complicated or not fully worked out, right?
You mean, we understand this via analytic continuation to Euclidean theory, but there is a way to analytically continue to Lorentzian for unitary theories, and this is kind of understood, I would say.
I would say it's well understood by this stage, actually, sort of the mapping between what you'd have as your Schrödinger-Kelvin contour and your order of operators and how you'd map that over holographically.
I thought that there was this interesting subsets of operators which are called null ray operators, which singularities are very, they are not Euclidean.
But these are understood. This is about the details, right? There is a theorem of Servarle-Schrader that has been revisited in the context of the CFT. And now the details of this theorem tells you can do the analytic continuation, but what will happen after you analytically continue? Of course, you will have a bunch of light cone singularities, but these are all fixed. Okay. And there is, just to understand the details of what happens. Then this is about light ray operators, and there is a lot of physics that you can extract from them, a lot of calculation that you can do. But from a conceptual perspective, there is no more than that. This is kind of the theorem that is not explicit, if you want. So, given this,
Massimo, so this becomes clear when in holographic context where the boundary and the bulk share a time direction, but when this is not so, then...
I will get there. Okay. I want to get there, and this is the point. So maybe I'm being a bit slow, but it's good to stimulate some questions. That's what I wanted to do. Okay, so the question is if we can generalize this understanding and how this OP and crossing gets generalized beyond the picture, the very nice picture of AdS-CFT. But let me make some comments to set a bit the stage. Is that in AdS there is no S matrix. So we are all used to work with S matrix in quantum field theory in flat space, but in AdS there is no S matrix because there are no free asymptotic states. So this is something we have to live with, and this is something this axiom live very well with. So this is just a comment. And the way AdS-CFT replaces the S matrix is with these boundary correlators, which in some sense are a little bit different than S matrix because they are off shell. They are objects that live naturally off shell. And the main observables, and yes, so another comment that is a bit technical, I will not really go into the quantum gravity. I will focus most on quantum field theory, because already here is not that easy. Okay, so from now on, let me put this in quotes, and let me move to kind of quantum field theory, where we understand very well the holographic dictionary. So what are the observables that we focus on holography? They are this kind of boundary correlators. And they are obtained via some type of extrapolate dictionary. So you take some limit at the boundary. So Z is the standard Poincaré coordinate of some bulk time-ordered correlator of the fields that live in the bulk. So the field theory picture is easier to understand kind of the rules of the game, because okay, in the quantum field theory case, these are not all, so when I take the limit, these are not all the observables of the quantum field theory. So we are just looking at a subsector of the observables, but these are nice, this is a nice subsector of the observables. And this is the subset of the observables that extends to gravity, to the gravity case. So we lose all the other observables in gravity, but we kind of keep these observables. And in the gravity case, this object is replaced by some quantum gravity partition function with Dirichlet boundary condition. And this is very important. Okay. In quantum field theory, we have local observables that live inside the bulk. And when we take this boundary limit, we kind of lose them. We don't look at them anymore.
To compute everything.
Yeah, but here, you see, only in the gravitational case, this is the full gravitational path integral. Technically, there are observables that exist inside that you don't have in quantum gravity. So this is just a technical subtlety.
Just so if you understand, suppose that you have a full quantum gravitational theory in the bulk with a partition function. Okay,
yeah.
You computed the function integral, so these observables can be computed via the function.
In the case of quantum gravity, the claim is that these are all the observables.
Okay.
The local, I mean, it is all the observables. All the correlation functions that you may want to compute, they are these ones.
So they're not, so
there could be no local observables, which I'm not looking at.
Okay, so what is left is possible non-local. Okay,
yeah.
Thanks.
So let me now draw a picture. Because what we want to do is to generalize this picture. So I will draw all the spacetimes. We started from this nice cylinder picture, which is AdS, where all of this is kind of clear, and we define this type of observables. And it's important to stress that AdS is like a box. I mean, it is a cylinder. It's depicted like a cylinder precisely because it's like a box. And what does this mean physically? It means that time like geodesic, they stay inside. They never leave. That's also one of the reasons that you cannot define an S matrix. Actually, the distance from the center for some, here you can picture this as a type of bound state that is created if you have two particles in AdS. The distance from the center goes like the radius of AdS times log of the spin. So things are kind of confined inside this box, while light rays, they can reach out to infinity in a finite time. Okay? However, here in this picture, we never allow outgoing radiation. So this is not allowed, because if we would allow this, the theory would automatically become non-unitary, because then it could exchange a lot of information between the boundary, the things that go here, they could come back. We wouldn't be able to set up any meaningful physical problem unless we specify what is living here at the boundary. Okay, so this is an important feature of this picture, which is related to this Dirichlet boundary condition that we enforce. So now let's move to flat space, and let's draw the corresponding Penrose diagram here. I mean, there are some similarities and some differences, of course. So a similarity is that here, so the infinity, the point at infinity, so a difference is that the point at infinity now is like, but there is still some time-like infinity, some space-like infinity. So massive particle, they reach now infinity here in this point, and massless particle, they actually live, they go to infinity at scry. So there is some kind of similarity in the sense that on scry, like in AdS, the massive particle never go, only the massless particle can reach scry, but here we can define asymptotic states because we have this other point at infinity also for massive fields, and in general, people look for S matrix, because we can define asymptotic states. Okay. So this is the picture for flat space, and now there is another picture, another space-time, which share maximal symmetry, and that I want to mention here because I like. And this de Sitter. So if we change instead the value of the cosmological constant, we get a positive cosmological constant. Again, the asymptotic structure of the space-time changes drastically, and now the boundary does not live anymore at infinite space, but it lives in infinite time. So here I'm using again some Poincaré patch, and this is eta equals 0. This is the future infinity, and here is the kind of boundary where we can, where everything now goes. So the difference is that now everything, not only massless particle, everything reaches the boundary and flows out. Okay, so here nothing flows out. Here things must start flowing out. There is radiation flowing out, and here everything flows out. Okay? So another comment here is that this space in this matrix is manifestly out of equilibrium. Okay? Because the metric is manifestly time dependent. So the more we go from here to there to here, we lose equilibrium. This is also another comment that is kind of should be in the back of our mind for this talk. Okay, so let me now try to fill in this picture and say something more about unitarity and causality. Of course, here the group, in the case of Lorentzian anti-de Sitter space, the isometry is SOD, 2. And that's important for unitarity because we ask for the generator in a unitary theory to be Hermitian. And so the conformal boost and conformal and translations should be Hermitian operators. So this is unitarity here. And then the other important axiom that we want to study is causality. So this is unitarity. And then there is causality. So causality, as always, is kind of related to some analyticity property, and this is what I mentioned briefly before, and is about the type of the singularity. So the only singularity that can appear in these observables are when we cross the light cone, and they are completely fixed by conformal symmetry. So this is kind of analyticity, and this OPE. Basically, that's what That's what this is. So usually we don't formulate, though, physics in this language of Lorentzian and de Sitter, because we are used from quantum field theory to Wick rotate. This is very standard trick because we like partition functions, and partition functions for equilibrium systems can be computed in Euclidean signature. So we do a Wick rotation, and in the center, we go to this nice Poincaré disk that is the Euclidean anti-de Sitter space, where the boundary is naturally the circle at infinity. So this is the place where most of the results, the quantum field theory results, are under control. Okay, it's a similar picture to what happens in standard quantum field theory. The path integral with imaginary action, e to the is kind of not well defined mathematically. If you do a Wick rotation, you get a better path integral, you get a minus s Euclidean, and this we can attempt to make sense of. So we get here in this point. So what happens here when we get to Euclidean anti-de Sitter space? So what happens is there are various things that happens, because now the isometry is SOD plus 1, 1. But this condition here, when we analytically continue, it becomes a different type of condition. It's not anymore unitarity. So we are not asking a theory that is unitary in Euclidean anti-de Sitter, but we are asking for a reflection positivity. And this implies that basically P dagger is not anymore P, but is K, and K dagger, of course, is P, and this is at the basis of, at the root of the fact that the spectrum in this Euclidean theory has to be lowest weight. So this is the lowest weight condition on the Verma modules of the CFT, and is equivalent to the fact that the CFTs have discrete spectrum. So this is a huge simplification. And is what we are used to, because this is what describes standard Lorentzian conformal field theory. Okay? So this is the standard picture, but now we can attempt to see, so here we arrived here. Notice that this SOD plus 1, 1 is exactly the same isometry group of the boundary of de Sitter and of the celestial sphere. If we here you have R times SD, also here we have the Lorentz group, which is SOD plus 1, 1. So this space, as a base space, kind of shares these two examples as isometry. So in principle, one may think to analytically continue between this space here. And I want to discuss a little bit what happens. Now, the details of this analytic continuation is kind of the second part of my talk, if I manage to get there, which I hope so. But I want to at least give you the punchline of this. So there is an analytic continuation. Let's start from the de Sitter case. And this analytic continuation that maps de Sitter in the Euclidean anti-de Sitter space is eta equal to plus or minus IZ. So when we do this analytic continuation, we go from here to here. So what happens when we do that? Now, the funny thing that happens, and I'm referring to these axioms, causality and unitarity, is that unitarity is not anymore this one. So this is reflection positivity. So I think we should not call it unitarity somehow. People are used to call it unitarity, but is unitarity here? What we usually deal with is reflection positivity. Actually, when we do this analytic continuation, we do get unitarity of this group. So we do get that our generators have to be Hermitian with respect to the Lorentz group, SOD plus 1, 1, which is the Euclidean conformal group. And this is kind of the main difference. So this is make you think that the theory that we will get here, when we analytically continue them here, they will be radically different than the theory that you get when you analytically continue from Lorentzian anti-de Sitter. And this is also related to this Dirichlet, that we have to enforce here, and that here is a little bit more subtle, because this boundary the structure, the asymptotic structure of the boundary does not allow you to set up a Dirichlet boundary condition to start with. So this is unitarity, and this unitarity is to some extent the same that we would get from here also. There is an additional complication, is because here we don't not only, so unitarity of SOD plus 1,1 is a sufficient but not necessary condition for unitarity of the Poincaré theory. We should also enforce that the theory is Poincaré invariant. And this will have some additional condition. But on the celestial sphere, the unitarity will be the same. So when we analytically continue to Euclidean anti-de Sitter space. Yes? Well, I'm only asking that the evolution operator is unitary.
Which evolution operator?
I have some dynamics here in Minkowski.
You can, I mean, time evolution is really matching past infinity to future infinity. It's the evolution problem.
Yeah, but here I'm thinking, let's take an Hamiltonian. And I'm thinking in very basic terms, at this level.
So you are looking at the evolution of which fields? I mean, any, massless and massive?
Yeah, right now I'm not specifying any. I will be more detailed when I go in the next part of the talk. But if I have some concept of unitarity, which let's put it, let me answer you like this. So here we can have space-like slices. The Hilbert space on each space-like time slice has to be positive norm and the finite norm. That's what I mean by unitarity. And this unitarity here, when you extrapolate it to the boundary and you map it here, is this unitarity here, the unitarity of this group of SOD plus 1,1. I'm just talking about norm of states. Okay. Let's put it like that.
Okay, so the claim is that this condition not holds both from, this condition because you introduced talking about de Sitter, but the same condition is there both for the analytic continuation of de Sitter and the analytic continuation of flat.
Yeah, because what I'm saying is that the representation, the particle, or whatever representation theory of my quantum field theory that lives on de Sitter or on Minkowski is governed by this Lorentz group, is the same group, so they decompose into using Plancherel theorem, and what I want is that any state has to be positive norm. And this is just a statement when you analytically continue about this Hilbert space that lives on this slice, which is a Hilbert space on which SOD plus 1,1 acts. It will be more clear when I will introduce spectral representation, but this is the main statement. So, what is the bottom line of all of this? Is that we understand unitarity, and we start understanding analyticity. And this is the biggest problem in the field, because we can only control so far analyticity in perturbation theory, in the context of quantum field theory. We don't have, like in the case of CFT, a non-perturbative understanding of the singularity that we can encounter. So this is the kind of open problem, but we have done some progress in understanding this analyticity to all order in perturbation theory because of this analytic continuation that we have been able to define to all order in perturbation theory, and basically the analyticity structure of this, at least to all order in perturbation theory, looks very similar to the one in Euclidean anti-de Sitter, but with a proviso. So when we see this singularity here in the context of Lorentzian CFT, we get physical singularities, unitary representations. What we get here when we sit on some singularity, which is you would call OPE, or celestial OPE, or OPE in de Sitter, you don't sit, I finished this statement, you will not get a unitary representation, you will get something that we should think more like a quasi-normal mode, something that has some imaginary part. This is the generic situation. In de Sitter, we expect it's always like that because the expansion of the universe will break every bound state. In flat space, there could be stable singularities, but the picture is that this OPE should be interpreted more as like quasi-normal modes. I just made a statement. I explained analyticity here, and then I just made a statement about the properties of this here and here, which is true to all orders in perturbation theory, and it has the same analyticity structure as the analogous object here. Same analyticity structure, but different type of singularities, because while here the singularities are unitary, here the singularities are not unitary, and we should think them as quasi-normal modes.
Yeah, no, sorry, I wasn't clear. I meant when you're talking about analytic continuation from Minkowski to what actually? This I'm failing to.
To this space.
But
like here.
But are you thinking that this space is like the celestial sphere with a three-dimensional hyperboloid? Is it what
yeah, these are technical details which I will go through.
Yes, you're thinking of
foliating
Minkowski by some hyperboloid.
There is some foliation, and then you do the analytic continuation for each part of the foliation, and then you end up in the central point of the picture. And then you can analyze the analyticity structure, and you get, to all order in perturbation theory, a similar analyticity structure. I will give you examples.
I'm sorry, I'm thinking, it's not, I mean, if you're foliating by hyperboloid, it's not even an analytic continuation, right? It's genuinely, you have hyperboloid in Minkowski space, and genuinely a sphere at infinity, so it's not even, it's like genuinely the same group, as you're saying, it's SO31 that you're thinking of it in different way. Or am I misunderstanding something?
So, no, so when you do hyperbolic foliation, to end up only with the Euclidean anti-de Sitter space, you will get both de Sitter and Euclidean anti-de Sitter. You have to do some analytic continuation.
What it means, the hyperbola are already Euclidean AdS, right?
Some of them, not all of them. This one, yes. But this one, no.
It's the zero.
Okay.
It's de Sitter.
Yeah.
You also want
You have to analytically
ones.
continue. That's all I'm saying.
Okay, no, but okay. You're also
You
thinking of
cannot
this
avoid
others.
analytic continuation.
Okay, you also want to think of this de Sitter stuff. Okay.
And actually, a nice thing is that the continuation between de Sitter and Euclidean AdS is recycled here in Minkowski. You see, once you have the map in de Sitter, you
So what time is it?
say in Minkowski.
How much time do I have? 12. Good.
Just a question. It's a technical question, but just to see how you're gonna. The things we worry in celestial holography in flat space are the logs and the infrared divergences, which means that this Hilbert space is not normalizable.
You will see a log later. This is an example.
Yeah.
But what I mean, so I think I can anticipate this. What I mean by analyticity, to all order in perturbation theory, is a statement about the Fourier expansion of the correlator. So I have a correlator, let's say a 4-point correlator. And using just SOD plus 1,1 Plancherel formula, I can write this as an integral in my spectral parameter of some spectral function times the partial waves that are the plane waves of SOD plus 1,1. So now I'm talking about the singularity that can appear here. We know that this object, if we live here, has to be meromorphic and only with single poles. If there was a double pole, that would be a logarithm. Okay? We can claim that this is also meromorphic to all order in perturbation theory in these two cases. There are examples where there appear logs, but they could be spurious logs, perturbative artifacts. Logs appear also here when you use perturbation theory. The D function have logs, but they resum, because we know non-perturbatively they must resum to remove all the logs. That's an open question. That's what I mean when I say that here we don't know the non-perturbative structure of the singularities, but we can understand this rho of nu to all order in perturbation theory, and we know it's meromorphic at least. There is no log of nu or crazy other things.
So
No, it's not an axiom. We find that it's meromorphic by computing perturbation theory.
by resumming.
By resumming, looking at perturbation theory in all possible
In
details.
AdS, you mean.
This one is done both in celestial and in de Sitter. This statement you can formulate, you can make both in celestial and de Sitter. So this is the kind of the bottom line. That's what I mean by analyticity more concretely. Okay? So just to summarize this kind of big picture, is that AdS-CFT capture holography, and because of the Dirichlet boundary condition, it naturally captures holography for equilibrium system. Okay, there is nothing escaping, and the system is in kind of equilibrium with itself. Instead, the key difference that I want to underline with the sitter and celestial is that we have to allow this outgoing radiation. Actually, this will pop up in a very nice way in this analytic continuation that we cannot avoid, and I will underline it. And is related to the fact that somehow canonical ensemble is a bit, is what we like, but it works here very well. Here and here, canonical ensemble is a bit unclear, I would say. Okay, so let me now go, after this big presentation, if there is any other question about the big picture. Otherwise, I will try to give you some more details. So let me review what happens in the sitter and give a little bit more concreteness to my words about outgoing radiation, equilibrium, etc. So I want to start with the sitter because it's good to, I like exchanging these ideas from different fields. So I think I don't know how many of you are experts of the sitter. I'm sure some of you are. But the key point of the sitter is that in is not in-out. So this is also the basis of the fact that even in the sitter, there is no S matrix. And basically, the evolution operator from minus infinity to plus infinity of the vacuum is not a phase of the vacuum like we are used to in quantum field theory. So we cannot, I mean, in-out correlators are not the right language to use. So what we do, actually, use the right language to begin with, is this in that is also good for quantum field theory. And basically what you do is you have time, so you have to compute some vacuum correlator, but you have to understand how the vacuum is evolving. So the right thing to compute is to start from the vacuum, then evolve in time, put all of your insertion here at the time where you want to understand your physics, and then you cannot drop this time evolution, even in the limit where time goes to infinity. So you have to keep it. Okay, you cannot drop it.
Say something. Static patch, global vacuum, Bunch-Davis,
Bunch-Davis.
Hawking-Hartle, Bunch-Davis?
Bunch-Davis.
Okay, thanks.
You can also do, yeah, but Bunch-Davis. I don't want, this is also another technical problem that in quantum field theory you can have many vacua, etc. Some people think that these other vacua don't make sense. Some people, there are many claims in the literature, even very recent, but I don't want to go into these details. Let's say I have a nice vacuum. Okay, so this is, so usually when you compute S matrix and you do in-out, you drop this because you send the eta to zero limit, you go to infinity, this is equal to a phase of the vacuum, and then you get in-out, but you cannot do this. Actually, you have to integrate over both this time contour, and then you get the time-ordered e to the minus I integral from minus infinity 1 minus I epsilon. This is a standard way to get the vacuum in path integral to eta of the Hamiltonian, and then here you get the anti-time order piece. And of course, the I epsilon is flipped by the complex conjugation. So again, it's nice to have a picture of this to give you an understanding of the analytic continuation that now we will do. So we can work in the eta plane. Actually, I like more the minus eta plane because eta is always negative as a convention. So in the minus eta plane, you see we have time order and anti-time order. This means that there is a branch cut. And the I epsilon is precisely how you go around this branch cut. So in the initial part, in the time order part, you integrate below the branch cut. And in the other part of the contour, you integrate above the branch cut, and then you put some insertions here at the tip. So that's the picture in the minus eta plane. And now what we did with Charlotte was to see why we don't open up this integral in the complex theta plane, and we can deform it to this contour here. So this is the integration. So it is equivalent to open up this integration contour like this by defining z equal minus eta e to the plus I pi over 2, and here to define z equal minus eta e to the minus I pi over 2. So of course, as always in analytic continuation, you have to be careful about boundary terms, and you have to do these checks, and that's what we did using Mellin space, which I will not be able to discuss here, it's just technicalities. We show that you can do this analytic continuation for every Feynman diagrams that you can draw, or in this Hamiltonian. You know, you can expand in perturbation theory, you get Feynman diagrams, and you can do this. And now, what you get, is that you started from some partition function in the sitter with the doubling of the fields, because there are the fields that live on this contour, fields that live on this contour. This is the standard in formalism, and I call them phi plus and phi minus. And then we analytically continued perturbatively, so not for the full path integral, but perturbatively, we analytically continue this to some, see what happens here, I said it before, this is exactly the analytic continuation I wrote there. So this analytic continuation lands on some partition function now in Euclidean anti-de Sitter, so not in Lorentzian, in Euclidean anti-de Sitter, where the different fields have different boundary conditions. So there is some new field, new scalar, phi tilde plus, which will have this boundary condition, z to the d over 2 plus I nu, on the bound when you go to z to 0, times some function, that is the boundary condition. And then there is another boundary condition, phi minus, that goes, when z goes to 0, to z to the d over 2 minus I nu. So, what does this mean? So this is quite different than the standard Wick rotation that we are used. The Wick rotation is about partition functions. Here we are not doing that, right? We are doing something slightly different. We are just rewriting this integration contour, but we do get an Euclidean AdS partition function with two different fields and two different boundary conditions. Now, these two different boundary conditions, you see this plus I nu and minus I nu, they are the Neumann and the Dirichlet boundary condition for two different scalars. So they coexist. And the physical interpretation of these two boundary conditions is precisely the outgoing radiation that coexists with the actual CFT itself. So this partition function is actually, we would like to think, we can do this only perturbatively so far as some CFT plus radiation partition function, which of course should depend both on the boundary photons and on the conserved currents. And the boundary photon is one of the two boundary conditions, the conserved current is the other boundary condition. So this is radically different than AdS-CFT, the standard AdS-CFT.
Thank you. Yeah, in Minkowski, we are used to think that what the semi-classical limit of scattering amplitudes compute is some sort of evolution initial. I mean, it's compute some observable of an initial value problem from square minus to square plus. So here, what would be the semi-classical interpretation?
It's the semi-classical interpretation of any non-equilibrium system. You can compute correlation function at a given time.
But what's the evolution, so to speak? I mean, what do you fix? What's
the evolution is here. It's just that this is not a scattering process because we don't know how the vacuum, the in vacuum has to evolve too. It will evolve too into something. Yeah. We are working with conformal time eta. So technically speaking, from the observer of that lives in the sitter, this doesn't make any sense because he will not have access to this. Here we are just trying to understand the holographic screen of the sitter without really caring about what an observer can see. This picture has a physical meaning in the context of inflation, where we now are super observers of the inflationary epoch. That's where physically this is useful. But if you don't, I mean, also from the perspective of theoretical physicists, for me, this is an interesting picture to understand on its own.
So maybe my confusion is it's just you take some data on the boundary of the sitter, you evolve in time, and then you evolve back.
You start from the vacuum in the sitter. There is the evolution, the exponential evolution. This will create a lot of particles from the vacuum. There is particle creation, and then you try to understand what is the correlation function between these quantum fields in the future. This is the picture. So you have a system out of equilibrium, and you just let it evolve in time, and you try to understand the quantum fluctuations of all these components.
So you want to see that some initial data from...
Yeah, but
like in math.
Okay, so but the important thing here is that, and this can be also seen at the level of the propagator. So there are a bunch of propagators in the sitter, because you can propagate like this. Propagators are always off shell, so you can propagate in many different ways. And these propagators contain both Neumann and Dirichlet contribution. Okay, so this is another very big difference with the AdS-CFT. So somehow we shouldn't really take AdS-CFT so seriously, because actually what we get when we try to apply the same logic to the sitter and celestial holography is something radically different. What we can still use is the tools, okay? So this is the picture that we got in the sitter. I sketched it very much, but more or less there is an identity between these two partition functions that is valid at the perturbative level. And now I want to discuss something that maybe you are more interested, how this picture generalizes to celestial holography. And here we do have an S matrix, right? But in the two previous examples, we didn't have. I don't want to cancel this. Maybe I can do here. So what do we want if we want to generalize this picture? Let's forget about the S matrix. I want to be agnostic about, we have an S matrix, but I don't want to really use it. What I want is some analogous definition. I want to define some celestial correlator as some limit, which we have to understand, of time-ordered correlators.
Sorry, Massimo.
Yes, please.
Before we move on to flat, the phi tildes with the two boundary conditions, they are shadow transforms of one another, or?
No, they are different fields.
Okay.
There are two scalars. When you do this analytic continuation, there are two fields that propagate in your correlator. The shadow is a relation, is a non-local transform. Mm-hmm. No, they are really two different objects that you get when you do the analytic continuation.
Okay, thank you.
So we want something like this. We want to define something like this, where I would call this celestial correlator. So in the sitter, I started from the right object in the sitter, the in correlator, which was the only observable I had. So here, I want to start, therefore, from the time-ordered correlator in Minkowski, which is the analogous object in Minkowski. So and the question is how to make this picture meaningful. There is one problem, of course, that this lives in D plus 2 dimensions. This lives in D dimension. This is a funny feature of the celestial sphere that some people have been trying to understand using Carrollian physics. But let me stick to the celestial sphere. So how do we do this? And this is maybe will make clear some of the questions that were asked. We do this by doing hyperbolic foliation of Minkowski. So we get some, if we do the hyperbolic foliation of Minkowski, we get two Euclidean anti-de Sitter spaces. So this is this Euclidean anti-de Sitter, and also another one here. And then we get a big Lorentzian de Sitter space. Okay? We get the global, so we get actually two Poincaré patch, some D plus and D minus. Here we can call A plus and A minus. So we get 4 Poincaré patches when we do this. But again, we have also the radial direction. So how do we define this limit? And how do we make sense of a relation between something that lives on the celestial sphere and something that lives in D plus 2 dimension, 2 dimension more? And the trick is to basically do the radial reduction, which mathematicians call the Fourier transform on the cone.
Sorry, can I?
Who is asking?
Here. So your goal is also to describe null infinity eventually?
Null infinity is the light cone.
Yeah. Ah, okay, so you also include the light cone. Also.
No, I don't think, the light cone is measured 0. You can show that it doesn't contribute when you integrate. You can actually do, split the integral as an integral over A plus, and all the others, and of course in the radius of all these hyperboloids. You don't need to integrate explicitly on the light cone. The light cone is the point on scry. So when you go to infinity, the light cone is the celestial sphere. Actually, it's very nice because it puts AdS-CFT on kind of similar footing because this is exactly the ambient space approach to AdS-CFT. This is exactly the boundary.
So this is why this is more geared to talking about celestial correlators rather than Corollian correlators.
Yeah.
Because you directly go to the
sphere. Yeah. The null cone is in measure 0. So you have to integrate over every point in everything, right? But you can show that the integral is, you can do like without, there is no contribution from the light cone when you integrate. That is the boundary, so it's not really. So we should think of the light cone really as the celestial sphere that lives at infinity. The integration covers, the hyperboloids cover everything. So let's go back to here. So we have to, so let me write now the prescription. So we define a radial reduction of the flat space correlator simply as a Mellin transform, which, as I said, is the Fourier transform on the is some generalization of Fourier transform. So we take the time-ordered correlator and we do this radial Fourier transform. So what I get after doing this Fourier transform is that is a correlator that lives on this extended hyperboloid. X hat can be on any of these patches, A plus, D plus, D minus, A minus. Okay? And now we can define the limit. X hat lives on the hyperboloid, so it's 1 over z times something, and the limit is z to 0. And when you do take the limit z to 0, from each of these hyperboloids, you are actually reaching the infinity. Okay? So this is the physical picture. And this is what we call celestial correlators, not to be confused with the celestial amplitudes, which are the Mellin transform of the amplitude, but only for the massless case. This prescription of the radial Mellin transform covers both massive and massless case, precisely because we are off shell.
So you can also write down celestial amplitude for massive particles via these Bloch-to-boundary propagators.
Say again?
You can also write down celestial amplitude for
massive
massive
but they are not
particles.
Mellin transform, right?
No.
They are more complicated. Yeah. My comment is that this is the same Mellin transform covers all possible cases.
Is that you can apply similar prescription also for celestial amplitudes, right? So the external leg would instead be the Whiteman function, and you'll be performing the same Mellin transform.
Yeah, so basically, yes. So you can actually define, the comment of Charlotte is that you can actually rewrite the conformal primary wave functions for the S matrix as a Mellin transform, but instead of putting here the time order correlator, you have to choose different I epsilon prescription to be on shell, to have, so the Whiteman function, which is on shell.
You mean to write a massive celestial amplitude using just one transform, but then, yeah.
Yeah, if I would compute the massive Whiteman function and I would take the same Mellin transform, I would get something that is the celestial amplitude.
Yeah.
Celestial amplitude. Okay. So, how much time do I have? Because maybe I can go to some juice here.
Officially, I think 10 minutes.
10 minutes, I think is enough. I don't know if there are other questions or you want to hear about something, but since I have 10 minutes, I want to discuss an example where we know how to compute this rho of nu explicitly, perturbatively, of course, and we see what type of singularity appear and how simple is this celestial amplitude. This turns out to be very simple. Correlator, sorry. Right, I'm mixing things up now.
If you could just...
It comes from the analyticity structure of this correlation function. It's some kind of built-in. Because this is, so we know that from Whiteman axioms, these are some very nice analytic functions. And you can analytically continue everywhere. You get some I epsilon prescription, and you can actually analytically continue from the plus to the other boundary. Just everything is analytic.
Is here what the antipodal matching is replaced here by matching
by an I epsilon
Euclidean and the zeta that you analytically continue?
Yeah. Yeah. So basically, everything comes out of an analytic function with a given I epsilon prescription.
So the matching is at that one point that is a measure zero? Like,
yeah.
Is that,
Yeah. So let me go to this more concrete example, because I think I like the philosophy of shut up and compute rather than any other thing. So I like to see the results of this, and that's why we liked this prescription, because it allows you to get a lot of explicit results. So what I want to compute, what I want to discuss how to compute is basically a simple 4-point amplitude of this type. Let's say that everything is a scalar for simplicity. I don't want to enter into details, into other details. So I want to compute an exchange amplitude, and I want to compute the celestial correlator associated to this exchange. Let's I hope I will not miss it anymore. So what we get, and I mean there is a lot of technicalities here, but is that this can be written as an integral over only the principal series of some coefficients, which you would call OPE. Actually, they are not exactly OPE. So you get something that is manifestly factorized and can be written as an integral. Now this is the Poincaré disk of, this is the exchange in the Poincaré disk, where these are delta 1, delta 2, delta 3, delta 4. So this is an object we know very well, because we computed it many times in AdS-CFT. To get this, we just have to dress it with some functions, these C's. What these C's are exactly the 3-point function. So this is C of delta 1, delta 2, delta 3. So some function. Is a function of the masses in general. So in the case of massless, it's a number, or depends only on delta 1, delta 2, and delta 3, of the corresponding Witten diagram, 3-point Witten diagram. So we get these nice coefficients of the Witten diagram, and we can instantaneously write down the celestial amplitude for the exchange, and we get this. So now this is the exchange.
Sorry, the deltas refer to the bulk Lorentz group in Minkowski?
Delta refers to the scaling dimension of this transform.
Yeah. Because you've said before something about the relation to masses, but there's no relation to the mass.
Well, yeah, that's a nice thing, that's a nice comment. You see, in the case of the sitter, the relation to mass only allows two deltas, delta plus and delta minus, and that's what appears. In the case of celestial, because there is a reduction, a single mass allows the whole integral in delta. So they are all, because we are reducing from a bigger space to a hyperboloid, we get some kind of infinite continuous spectrum of exchanges here. Instead of a sum. So in the sitter, we would have just delta plus and delta minus. It's the same coefficients, and then only delta plus and delta minus there. It's a very similar thing. But this is not what we usually want in CFT to understand the OP structure. What we want is the conformal partial wave decomposition. So we want to replace this exchange with the plane wave of the conformal group. And this is a kind of nice, a bit tedious calculation. There are a lot of subtleties with the integration contour. You have to be careful to everything, subtractions. This is now in our paper, last paper of this year. It's all explained there.
What are the poles? What is C delta and the poles and the cuts there?
So they are all meromorphic functions.
Okay.
They are complicated.
And
there is an expression for C delta as a triple Mellin integral. They are kind of Appel function in the masses. When you take the massless limit, they simplify a lot. I will give you the result shortly.
And what's the physical meaning of the poles? Are they quasi-normal modes? Are they? So
I will get there. So to get a physical meaning, I have to get the partial wave expansion.
Okay. And just a question, you didn't mention the relationship with the S matrix, so this is the correlator. Do you have a LSZ?
Yeah, LSZ works. I mean, we wrote it in the paper.
But LSZ, usually you diagonalize the momenta, so it's, okay, you have a more complicated...
LSZ, so you have to multiply with the equations of motion, fix the momentum on shell, and fully transform back. We wrote it in the paper. We didn't give details. Details will appear very soon. Sebastian is working on the details, examples, but it works.
And you have a way to renormalize the mass, like to find the right poles on the boundary?
Yeah. So the LSZ of the celestial correlator gives you the perturbative celestial amplitude. Yes, I got it right. So
massless, if you try LSZ, you would recover these infrared divergences.
Here is a scalar theory. Yeah? We are doing, this example is a scalar theory. You can then do spin 1, spin 2. This is also in progress.
Okay.
We have slowed. So, but yeah, this is the simplest example just to. But let me get precisely to your point. No, we have this, but we want another thing. We want the same integral with some rho of nu and the plane waves. Now, if I am able to rewrite it like this, then these singularities will be the physical singularities, which I may be able to interpret as OP or quasi-normal modes. So we did this calculation in this paper from last February, and it's very nice what happens, because now let me draw another picture, is the nu plane. So we compute this rho of nu. I will not write it down, because still not super easy, but I will tell you what are the poles of this rho of nu. So there are actually 4 infinite series of poles, which we expect, some of them, some other we don't. So let me write it, as delta. So this is the delta complex plane. So now the poles that we find are, so this is the, there are infinite series of poles. There is one series like this, which starts at delta 1 plus delta 2 plus 2 minus d, where d is the dimension of the celestial sphere. And then inside, maybe I have another chalk. On the same line, there is another series of poles. Let me put it here. which are also integer spaced. And this is delta 1 plus delta 2. And then plus n, of course, plus n. To n, yes. Sorry. And then there is another similar series of poles. What did I? No, you have to, D is the dimension of the sphere.
That's why, in dimension for these two,
These two
series are the same.
That's the point where I want to get.
Poles.
There is a double pole.
There's a double pole.
We don't know if it is an artifact of perturbation theory, but I will comment about this. So we get another series of poles, not necessarily symmetric. Here is delta 3 plus delta 4 plus 2 minus d, and then there is the analogous delta 3 plus delta 4 plus 2n, also plus 2n. So you get these two infinite series of poles. So this is the generic case where the exchange scalar is still a massive scalar. And something even more drastic happens when the exchange scalar is massless. Okay? When the exchange scalar is massless, where do I have a nice white chalk? So this is, okay, first comment is that this cannot be really real OPE because delta 1 plus delta 2, if delta 1 and delta 2 belong to the principal series, delta 1 plus delta 2 does not belong to the principal series. So the right interpretation is that there is some imaginary part, so it's a quasi-normal mode of the theory. There is something happening of this type which we don't really understand yet. But
the dimension of the light, I mean, the light-rays operator will do that, right?
He's considering principal series.
Maybe that's a...
Also, all of these tower of operator have shifts, but the question is the real part. The first, yeah.
Oh, you mean the Earth?
Yeah. So nu is, the imaginary part goes here, and it should be d over 2. That's the principal series. You think of an OPE when the state is physical, and physical is principal series here, because we are using the unitarity of SOD plus 1, 1. So technically, the states will not be unitary from the perspective of the celestial CFT. And what I was saying is that something nice happens in the massless case. In the massless case, you may think you have an infinite number of double poles, because, I didn't say, these are the usual double trace poles. This happens all the time. So this delta 1 plus delta 2 are analytic contributions to the exchange. They appear all the time in AdS-CFT. We expect them. This delta 1 plus delta 2 plus 2 minus d, you should think of it as in AdS-CFT, you have nu squared plus delta minus d over 2, where this is related to the mass. So somehow, this plays the analog role of the single trace operator exchanged in the exchange. That's the way it appears. Now, when the mass goes to 0, there is some identity between delta 3, delta 4, delta 1 plus delta 2. There are some zeros that come from interference between the different patches. I didn't write explicitly, there are some sign functions that come from interference. Basically, instead of having an infinite number of double poles, you just get one double pole. And basically, you can write down a closed form expression for this exchange where everything is massless, which is extremely simple, and this G, the conformal block. I'm writing, read the conformal block, delta 1 plus delta 2 dimension, and external dimension, delta 1, delta 2, delta 3, and delta 4, plus the derivative of the conformal block with respect to delta. Yeah, this is d equal to, sorry. I also, yeah, I'm d equal to because I'm considering the case of double pole. Evaluate the delta equal delta 1 plus delta 2. Plus delta 1, delta 2 replaced by delta 3, delta 4. So it's just this simple sum of two conformal blocks and two derivatives, which gives the celestial correlator in this case. And this derivative gives you logs in U, in the cross ratios, which we don't have in AdS. We never have them at this level. Logs come from cross-channel in anti-de Sitter space, and they should resum to give anomalous dimension. So we don't know if these logs should also resum and give anomalous dimension to this operator, and this is part of the non-perturbative type of singularity that we have. I think I will just conclude by saying that so there are two types of objects that we are used to. There is S matrix that exists that people are like in flat space. And it's exactly, why we like it, because it's what we measure at LHC, basically. But there are also other objects like these boundary correlators. And that's what AdS-CFT likes. So these boundary correlators that I discussed in QFT is exactly what will be the observable of a quantum gravity theory, at least in that AdS-CFT picture. So these are two objects, S matrix and boundary correlators. They are connected. But it seems that these boundary correlators, not the amplitudes, are maybe more general. They are definitely very simple. And why not formulating the celestial holography also, like in de Sitter and anti-de Sitter, in terms of these celestial correlators? Thank you.
Questions?
Can you relate those correlators to the approach of Per Krause and Richard Meyers with the partition function? Because now, as you say, you bring flat space and celestial holography in a more similar fashion than AdS, and I think their attempt was very similar. Although admittedly they were Carolian and not celestial, so maybe that's the subtlety, but have you thought about generating this coloration from the partition function that they defined?
No, I haven't thought about that.
Okay.
It could be interesting to think about it in that way, but I haven't thought about it.
Okay, thanks.
More questions? We're a bit over time, but if you have more questions. No?
I mean, okay,
please
maybe
ask, shoot the question.
It's more of the connection. So one of the organizing principle, let's say, in the celestial are really these infinite tower of symmetries. And people have shown that, in fact, they appear in de Sitter and AdS. People miss it, right? So it seems that there's this tower of symmetry. They're mysterious. So, and they're related to these poles, in fact. The Goldstone, in fact, the Goldstone and the memories are kind of another basis. People have shown that you can use this discrete thing as a generalized notion of basis if you use a pairing. So where does these symmetries plays a role? Where would it be there? So that was what was kind of useful to go to the celestial sphere, is to kind of identify the symmetry. Now it should be there in some form.
Yeah,
do you understand?
It should organize these poles. So
yeah.
This is also something we are basically, so the point is that these poles you should think of as some, from the perspective of Euclidean anti-de Sitter space, they are just conformal blocks. But they are big multiplets. They reconstruct some bigger multiplets. So this is the way you should think of these poles. They are required by the action of the symmetry. Okay. For instance, translations. Translation is there, it's not manifest, because we have fixed the origin of the light cone. But the translation is there, and that will tell you, if I have the first pole, I must have all of them. Mm-hmm. Mm-hmm. So that's how the symmetry will play with the spectrum of these poles in rho.
Yeah, there should be related to some word identities, but you have a concrete way to extract. I mean, let's say the thing I was saying, for instance, you have this tower of equations of motion, and they are kind of they correspond to identities or Schwinger-Dyson types of identities that organize in conformal dimensions, and so.
Here we are already quantizing, right?
Yeah, so even at the quantum level.
So the question is important. So this word identity will put constraints on where these poles can be and on what the multiplet will be. Here, somehow, the difference between de Sitter and flat holography is that the celestial sphere is a reduction. So you don't see all the symmetries when you go to the celestial sphere, like I mentioned, translations. And the spectrum, though, will organize into representations still of the Poincare symmetry and whatever generalization. I don't know if I understood the question. Or...
Yeah, I mean, we know now that the LW infinity symmetry algebra acts on de Sitter, I mean, on whether it's flat space or etc. It's kind of so I was wondering whether you have you know how it acts on your celestial correlators. Like, do you have a definition of the action of the symmetry
so
group?
you're asking if we have written down the word identities.
Yeah.
We haven't yet written down the word identities, but they will be, I mean, we are in progress to that.
More questions? Okay, if not, let's thank Massimo again for a wonderful lecture.